Welcome back to the session on the course of wave optics. Okay, today we are discussing about the fourth chapter in wave optics, which is nothing but aberrations and fiber optics. Okay, I am Prakash, belonging to Department of Physics, K.B.N college. Okay, let us go into the session. In this session we are going to see about introduction to aberration, what are aberrations, how they are classified, and then we are going to see about the chromatic aberration, spherical aberration, coma, astigmatism, and then curvature, and then distortion. Okay, in this these are the 7 topics that are related to the aberrations, and also we are going to see how these aberrations have nothing but the defect of a lens can be eliminated or it can be minimized. What are the steps you need to take in, what are the methods that are present, we are going to see in this session. Then coming to the fiber optics, we are going to see about the introduction to fiber optics, what is the principle of fiber optics, which is nothing but total internal reflection, then how the structure of fiber optics will appear, then what are the types that are present in fiber optics and what are the classifications, on what classification they have been divided, and then we are going to see about the advantages of optical fibers. Okay. Then coming to the aberrations, which are nothing but, as I said, defects of a lens. Okay, aberrations nothing but in general the equations of a lens derived based on the assumptions like all the incident rays make small angles with the principal axis. And the second point is the aperture of the lens is small and a point object will give a point image. Based on the 3 assumptions, the equations derived for a lens. But lenses are used to form images of points situated off the axis also. Okay. Then in general, what is aberration means the deviations from the actual size, shape and positions of an image as calculated by simple equations are called aberrations. Okay, the deviations from the actual size, shape and position of an image as calculated by simple equations, as I said, based on the 3 assumptions derived, those equations are called aberrations. Okay, which are nothing but defects of a lens, we'll call defect of a lens. Then aberrations are classified based on the 2 categories, that due to light, okay, then due to optical system. These are the 2 categories that the aberrations are classified. Then coming to the aberration due to light, if the light is not monochromatic, which means that it is a white light which you will be having a range of wavelengths, then the image becomes multicolored. As you know that the white color will be split up into 7 colors. Then, as I said, if the light is not monochromatic, then the image will become multicolored, and this defect is known as the chromatic aberration. Okay, chromatic aberration. Then coming to the optical system, even though if the light is monochromatic, which is nothing but the light is having a single wavelength, it is a single color, then several defects in shape of the images are found. There is a defect in the shape of the image, then they are known as spherical aberration. Okay, chromatic aberration arises due to light, and the monochromatic aberration will be arises due to optical system. These are the 2 categories aberrations are classified. Again, in monochromatic aberration we have classifications like what is spherical aberration, coma, astigmatism, distortion and curvature. How these aberrations will appear and what are the elimination and minimization methods that are present, we are going to see in this session. Okay, then we'll see step by step, like how the aberration will be formed, what are the reasons behind this aberration, and what are the elimination methods or minimization methods that are present. Okay, first we will see about the chromatic aberration. Now, chromatic aberration, we know that the refractive index varies with color. Then we know that the refractive index of violet color is greater than the refractive index of red color. Okay, refractive index of violet color is greater than the refractive index of red color, which means that the focal length of red color is greater than the focal length of the violet color. if you place a screen at the focal length of the violet color, the screen on will appear, the center will be violet color and the remaining will be of red. If you place the screen at the focal length of the red color, the center will be red and the remaining part will be violet. If you place the screen in between the focal length of the violet color and the red color, the image will be blurred. Actually, this defect is known as the chromatic aberration. Okay, the violet rays will meet near the lens and the red rays will meet the rays away from the lens. Here you can see violet color will rays meet first and then the focal length of the red color. The image of white object, as I said, here we are taking white light, okay, is colored, either colored or blurred. This defect is known as the chromatic aberration. Okay, the image of white object formed by a lens is colored and blurred. This defect is known as chromatic aberration. Now, as a chromatic aberration is classified into two types: longitudinal chromatic aberration and lateral chromatic aberration. Okay, here in this diagram you can see if O is a point object which is placed on the axis then it will be emitting a white light. The light falls on the lens, then IV is a point where all the rays of violet color rays will meet, and IR is the point where the image of the red color will appear. The formation of the images of different colors in different positions along the axis is known as longitudinal chromatic aberration. Okay, the distance here you can see the distance between the IV and the IR. Okay, the distance between the IV and IR, which is nothing but IR minus IV, will give the longitudinal chromatic aberration. Okay, longitudinal chromatic aberration. Then coming to the next type, lateral chromatic aberration. Okay, in lateral chromatic aberration we will take an object like BA, or AB is an object. Then here you can see on the right side BV and AV is the object, I mean nothing but the image of the violet color, and BR and AR is the image of the red color. Okay, BV and AV is the image of the violet color, BR and AR is the image of the red color. Here you can see that the object and the image are inverted. Okay, the object and image are inverted, and more even you can see in the there is a difference in the height of the image of the red color and the violet color. Okay, red color image is greater than of the violet color image. The images of different colors are formed of different sizes. Okay, the formed images are of different sizes. This defect is known as the lateral, or you can say transverse chromatic aberration. Okay, lateral, or you can say transverse chromatic aberration. The difference between these sizes of the images will give the lateral chromatic aberration. The difference of these sizes of the red color and the violet color images will give the lateral chromatic aberration. Now we will see this defect. Okay, how this is the defect. The images is either colored or blurred. Then we are going to see how we can reduce this defect. Okay, which is nothing but achromatism. Okay, this defect can be minimized. The chromatic aberration can be minimized by using the phenomena of achromatism. Okay, achromatism is nothing but when two lenses are placed in such a way that the image formed is free from chromatic aberration. The image should be free from chromatic aberration. Then this combination is known as achromatic combination, and the phenomena is known as achromatism. Then the images formed by a convex lens is different to that of the chromatic aberration formed by a convex lens. Okay, for suppose the chromatic aberration due to a concave lens is positive and the chromatic aberration due to a convex lens is negative, which is our of opposite. By suitable combination of concave and convex lenses, chromatic aberration can be minimized. it can be minimized. Such combination is known as the achromatic doublet. Okay, such combination of the concave and convex lens in such a way that the formed image should be free from chromatic aberration, then that phenomena, that combination is known as the achromatic doublet. Okay, again, achromatic doublet or achromatism are of two types. When the two lenses are placed in contact, which is nothing but it can be the objectives of this lens is that used in microscopes and telescopes as objectives. Then the achromatism for the two lenses which are separated by a distance, which is used for the eyepieces of the optical instruments. Okay, then now coming to the first one, achromatism for two lenses which are in contact. Okay, two lenses which are in contact. Here in this diagram you can see f1 and f2 are the focal lengths. F1 is the focal length of the convex lens and f2 is the focal length of the concave lens, and omega 1 is the dispersive power of the convex lens and omega 2 is the dispersive power of the concave lens. Then we know that the combined focal length, which is represented by capital F, is given by 1 by capital F is equal to 1 by f1 plus 1 by f2, where capital F represents the combined focal length, f1 and f2 are the focal lengths of the convex and concave lenses respectively. If we go on solving this derivation, we will get to the conclusion that the ratios of the focal lengths is equal to the ratios of the dispersive powers with a negative sign. Okay, f1 by f2 is equal to minus omega 1 by omega 2. The ratios of the focal lengths is equal to the negative sign of the ratios of the dispersive powers. So nothing but omega 1 by omega 2. The negative sign represents nothing but the one lens is a concave lens and the other one is a convex lens. Okay. Now coming to the second one, achromatism for the two lenses that are separated by a distance. Here you can see the two lenses are separated by a distance f1 and f2. Okay, with the distance is represented by small letter d. D is equal to average of f1 plus f2 by 2, where f1 is the focal length of the focal lengths f1 and f2, and omega 1 and omega 2 are the dispersive power of the two lenses. Then in this case the combined focal length capital F is given by 1 by f is equal to 1 by f1 plus 1 by f2 minus of x by f1 f2, where x is the distance between the two lenses. Okay, where x represents the distance between the two lenses. Then if we go on deriving this, we will get a solution like x is equal to x, which is nothing but the separation between the two lenses is given by the average of the two focal lengths f1 plus f2 by 2. This is what the achromatism for two lenses separated by a distance. Okay, now this is what about the chromatic aberration, and achromatism is the phenomena that the chromatic aberration can be minimized. Now coming to the next one, due to optical systems which is nothing but monochromatic aberration. This is the first one. In monochromatic aberration, this is the first one, which is called spherical aberration. Spherical aberration. Okay. The spherical aberration, if IM is where all the marginal rays will meet and IP is the point where all the paraxial rays meet, the image in between these points is not sharp. Okay, it will be not sharp at any point. The failure or inability of the lens to form a point image on an axial point object, which is nothing but the point, an object which is placed on the axis, that to a point object. This defect is known as the spherical aberration. The failure or inability of a lens to form a point image even though object is placed on the axis, that to a point object. This defect is known as the spherical aberration. Okay, the reasons for this is that all the marginal rays will meet at IM and all the paraxial rays will meet at IP. The image is not sharp at any point. Okay, the lenses can be supposed to be divided into circular zones. Okay, this is due to the fact Then the focal length varies with the radius of the zones. The distance between the IM and IP, the point where paraxial and marginal length is a measure of the longitudinal spherical aberration. Okay, it is the measure of longitudinal spherical aberration. The size of the disc is minimum in the position AB. Here you can see in the position AB the size of the disc is minimum, which is called as the circle of least confusion. The radius of the circle of least confusion gives the lateral spherical aberration. The circle of least confusion will give the lateral spherical aberration, or you can say transverse spherical aberration. The distance between the IM and IP is a measure of the longitudinal spherical aberration. Okay, if we say marginal rays, the rays which will pass to the rim of a lens are called as the marginal rays, and the rays which will pass close to the axis are called as the paraxial rays. Okay, the lenses can be supposed into different circular zones. As I said, the size of the disc is minimum at AB, which is called as the circle of least confusion. The radius of the circle of least confusion will give the lateral spherical aberration. Then coming to the minimization of spherical aberration, coming in chromatic aberration, there is only one method, that is nothing but the achromatism. But coming to the spherical aberration, it is divided. There are like 6 methods we can minimize the, or you can eliminate the spherical aberration. The first one is the spherical aberration can be minimized by means of stops. By placing the stops, we can minimize spherical aberration. And it can be, the spherical aberration can be minimized by the use of a plano-convex lens. Okay, and it can also be minimized by using the suitable lenses in contact, and it can also be minimized by using crossed lenses. And the next one is the spherical aberration can be minimized by using 2 plano-convex lenses separated by a distance. You can see 2 plano-convex lenses which are separated by a distance. If you derive this thing, you will get the distance between the 2 plano-convex lenses will be equal to the difference in the focal length, where f1 is the focal length of the first plano-convex lens and this f2 is the focal length of the second plano-convex lens. Okay, these are the methods which are used for the minimization or elimination of the spherical aberration. Now coming to the second aberration in monochromatic aberration is coma. When the point object is situated slightly off the axis, okay, if the point object is situated slightly off the axis, the image of the point object formed by the lens is found to have an egg-like comet shape. It will be in comet shape. This defect is called coma. Okay, here in this diagram you can see the point object is situated slightly off the axis. It is placed off the axis. The image of the point object formed by the lens is found to have an egg-like structure. Then this defect or this aberration is known as the coma. If you consider an off-axial point A, which is nothing but the object OA, we consider the image of A at the different zones of the lens, where I1, I2, I3. The rays leaving the point A will passes through the different zones, where 1, is one zone, 2, is one zone, and 3, is the other zone. And they are brought into focus at I1, I2 and I3. The 1, rays will meet at I1, 2, rays will meet at I2, and the 3, rays will meet at I3. So the image is not focus. The main reason for the arrival of coma is that different zones of the lens produce different lateral magnification. Different zones of the lens will produce different lateral magnification. And the other reason for this is each zone forms image of a point in the form of a circle. Each zone will form the image of a point in the form of a circle. These are the 2 reasons for the aberration called coma. And the elimination methods for the coma is that the coma will be minimized by using proper stop placed at a suitable distance from the lens. They should be placed at a suitable distance from the lens. and by designing lenses of suitable shapes and materials, they are designed for suitable shapes and materials. And Abbe is a scientist. Okay, Abbe showed that the lenses are completely free from spherical aberration. They are free from spherical aberration and coma if the following sign conventions are satisfied. If you follow these conditions, the formed images will be free from spherical aberration and coma. The relation is given by mu1 y1 sin theta 1 is equal to mu2 y2 sin theta 2, where y1 and y2 are the lengths of the object and images for the zone, and theta 1 and theta 2 are the angles which the conjugate rays makes with the axis. Okay, which the conjugate rays makes with the axis, and mu1 and mu2 are the refractive indices of the object and image. If you follow these three methods, we can probably eliminate or minimize the coma aberration, coma defect. The next one in the monochromatic aberration is the astigmatism. This is also somewhat similar to the coma. When the object or point object is slightly far off the axis, okay, which is placed off the axis, here you can see, the image formed by the lens is not a perfect focus, not in a perfect focus. The image consists of two mutually perpendicular lines separated by a finite distance. Okay, this defect is known as astigmatism. This defect is known as astigmatism. Here you can see meridian plane. Meridian plane means the plane containing the optic axis O and the principal axis is known as the meridian plane, and the plane which is perpendicular to the meridian plane is called as the sagittal plane. Okay, M1 M2 is the meridian plane and S1 S2 is the sagittal plane. Now coming to the reasons for the astigmatism is, if the screen is placed between M and S, where M is the point where all the meridian lines will meet and S is the point where all the rays which passes through the sagittal rays will meet. If the screen is placed in between the M and S, an irregular patch of light is observed. Okay, an irregular patch of light is observed. When the screen is moved between S and M, the patch of light reduces to a circle. It will be reduces to a circle which is called as a circle of least confusion. The difference between the M and S, okay, the point where meridian lines and sagittal lines meet, the difference between M and S is a measure of the astigmatism, and it is called as astigmatism difference. It will be called as astigmatism difference. Now we are going to see about the minimization or elimination of astigmatism. The astigmatism can be minimized or it can be eliminated by placing stops in a suitable position. Okay, they should be placed in a suitable position. Only the less angled rays are allowed to form an image. A suitable convex and concave lens separated by a distance. Okay, by this method also we can eliminate the astigmatism by a suitable concave and convex lens separated by a distance. And the other one is, for a system of several lenses, the astigmatism may be eliminated. It may be eliminated by adjusting their positions. These are the methods by which we can eliminate the astigmatism. Now we are going to see about the next one in the monochromatic aberration, which is nothing but the curvature. Curvature. Even when the lens is free from spherical aberration, coma, astigmatism, the image of an extended plane object, here you can see the image of an extended plane object OO dash is curved. If the screen is placed at I perpendicular to the axis of the lens, then the image is II dash will not in a focus. It will not in focus, but this is curved. Okay, this defect, this curvature, this curve is known as the curvature aberration, curvature defect. This is due to the fact that paraxial focal length is greater than the marginal focal length. This is the reason for which the curvature aberration arises. which is nothing but the paraxial focal length is greater than the marginal focal length. The minimization of this curvature is that the curvature can be minimized. For a simple thin lens, the defect of a curvature may be reduced by placing an aperture in the suitable position in front of the lens. In front of the lens. From a single lens, the curvature may be eliminated by giving it meniscus shape and using a stop placed in front of. The curvature can also be minimized, or it can also be reduced by combining suitable combination of concave and convex lenses of different materials. These are the methods in which we can minimize or we can eliminate the curvature. Then the last aberration in monochromatic aberration, which arises due to the optical systems, that is distortion. Coming to the definition, the image of a plane square-like object. The image of a plane square-like object placed perpendicular to the axis of the lens is not of a same shape. That is, it is distorted. It will be distorted. This defect is known as the distortion. The reason or this aberration arises due to the fact that same lenses produce different magnification for different axial distances. For different axial distances, the magnification will be different. The distortion is classified into two types. They are barrel-shaped distortion. The other one is the pin-cushion distortion. Pin-cushion distortion. Okay, here you can see, if you place this rectangular shaped mesh in place or in front of a convex lens, the image formed will be on a shape of barrel shape. Here you can see, if you place a square like object, the image is of a barrel shape, then this distortion is known as the barrel shaped distortion. If you place a square like object in front of a convex lens, then the image formed due to this aberration, if it will be in this shape, then this distortion is called as the pin-cushion distortion. These are the difference between the barrel shaped distortion and pin-cushion distortion. Now coming to the minimization of distortion or elimination of the distortion, the defect of distortion can sufficiently be minimized by taking thin lenses. By taking thin lenses, this aberration can be minimized, and a stop is placed between the symmetrical lenses so that the pin-cushion distortion produced by the first lens is eliminated by the barrel-shaped distortion produced by the second lens. These are the two methods that are available to minimize or to eliminate the distortion. Now we are getting into the fiber optics session. Okay. Let us see about the introduction to fiber optics first. First of all, let us discuss about what is an optical fiber, what is optical fiber communication. Okay, fiber optics is a technology related to the transportation of optical energy, which is nothing but the light energy, in guiding media, especially glass fibers. Okay, transportation of information through electrical energy is existing, but this optical fiber means transportation of information through light energy. Okay, because light will be having a speed of 3 × 10⁸ meter. That is the main advantages of using the optical energy as a guiding media. Okay, it is called as the optical fibers. Now coming to the optical communication, the communication through optical fiber is called as a light wave communication. Okay, the communication through optical fiber is called as the light wave communication or optical communication. Now coming to the optical fiber, optical fiber is a long hair thin transparent dielectric material. Okay, it is of a hair thin material made of glass or plastic. It is either glass or plastic, which carries the electromagnetic waves, nothing but the light, which carries the light waves of optical frequencies from one end to other end, is called as the optical fiber. Okay, Now coming to the principle involved in optical fiber, here you can see in this diagram the principle involved in optical fibers is the total internal reflection. Okay, before getting into the total internal reflection, we should know about the total internal reflection. When the angle of incidence is greater than the critical angle, the light ray does not enter into the denser medium to radar medium. It will reflect into the denser medium. This phenomena is known as total internal reflection. Okay, here the optical fiber in such a way that the core should be of the lesser refractive index as compared to the refractive index of the cladding. Okay, it should the core, suppose if you take core refractive index as 1.7, the cladding refractive index should be less than that of the core. If this adjustment can be made in the construction of an optical fiber, then we can achieve the total internal reflection. Even though if you turn or bend the optical fiber, the optical energy will not be lost. Now coming to the structure of an optical fiber, the structure of optical fiber can be divided into three parts. They are core, cladding and coating. These are the three layers that an optical fiber consists of. Now coming to the core, the innermost region of the fiber, which is made of either glass or plastic, is called the core. This is the area where the light transmission will happen. This is the place where the light will travel in the optical fiber. Now coming to the diameter of the core, it should be in a range of from 5 micrometer to the 100 micrometer. Okay, it should be having a diameter of 5 micrometer to the 100 micrometer. Now coming to the cladding, the layer which is present above the core, the cylindrical shell of glass or plastic that surrounds the core is called as the cladding. The layer surrounding the core is called as the cladding. The refractive index should be less than that of the core. In compared to the core, it should have a lesser refractive index. The function of this cladding is to provide a lower refractive index at the core cladding interface in order to make the light rays to reflect. Why? Because as I said that the principle of optical fiber is the total internal reflection. The light ray should reflect in the core itself, so that the core should have more refractive index than that of the cladding. The diameter of the cladding should be taken in of the order of 125 micrometers. Okay, now coming to the coating, which is a layer which is present around the cladding. Coatings are usually multi layers of plastics applied to preserve the fiber strength, absorb shock and provide extra protection. Okay, these buffer coatings are available from 250 microns to 900 microns. Okay, these coatings protects the core and cladding from the atmosphere. Okay, it is also called as the buffer coating. Now these are the structures. Okay, these are the parts that involves in the structure. Now coming to the different types of optical fibers. Optical fibers are classified based on the two categories. Okay, optical fibers are classified based on the two categories. The first one is based on the number of modes of propagation, how many light rays can enter into the core, and the second one is based on the refractive index profile. Okay, second one is about the refractive index profile. Now coming to the number of modes of propagation, the optical fibers are classified into two types based on the number of modes of propagation. The first one are called as the single mode fibers, which is nothing but SMF. The second one are called as the multi-mode fibers. The second one are called as the multi-mode fibers. Okay, based on the number of modes of propagation, the first one is called as the single mode fibers and the second one are called as the multi-mode fibers. Then coming to the based on the refractive index profile, the optical fibers are again classified into two types. They are called as the step index fibers and the other one are called as the graded index fibers. Okay, step index fibers and graded index fibers. Now we are going to see what is a single mode fiber, how it can be constructed, what is a multi-mode fiber and how it can be constructed. Okay, now coming to the classification based on the number of modes of propagation, we know that the optical fibers are classified into two types. The first one is single mode fibers. Okay, the single mode fibers having the characteristics that are of a smaller core diameter. Its core diameter should be of an diameter of 5 micrometers and the cladding diameter should be of a 70 micrometers. Okay, the refractive index of the difference between the core and the cladding is very small. Only one mode will propagate into the core. Those fibers are called as the single mode fibers or SMF. There will be no dispersion phenomena will happen in the single mode fibers, which means that there is no loss of signal. The single mode fibers are used for the long distance communication. The optical source that will be used in single mode fibers is lasers. Okay, lasers is the optical source that will be used in single mode fibers. It supports larger bandwidth. The single mode fibers will support the larger bandwidth. The launching of optical power into the fiber is difficult. Why? Because the core diameter is small. This is the reason why, because the optical power entering into the fiber will be difficult. Now coming to the fabrication or manufacturing of single mode fiber, it is difficult. Okay, why? Because it will be having smaller core diameter, hence they are more costly. Okay, now coming to the multi-mode fibers, the core diameter should be in a range of 40 micrometers. The cladding diameter should be of 70 micrometers. Here you can see the difference between the single mode fibers and the multi-mode fibers. Okay, there should be have a larger refractive index difference between the core and cladding. The number of modes they can propagate into the core. Why? Because the core diameter is more. This is the reason why, because of which more number of modes can propagate into the core. Okay, there will be more dispersion. There is a loss of signal in these fibers, in multi-mode fibers. These will be used only for short range communication. As I said, in single mode fibers the optical source is laser, but coming to the multi-mode fibers the optical source is LED. It supports the larger bandwidth. Okay, the multi-mode fibers will support the larger bandwidth. The launching of optical power into the laser is easy. The fabrication is less difficult, hence they are cheaper. Okay, the fabrication is less difficult, hence they are cheaper to manufacture. Okay, then they are cheaper than the single mode fibers. Now coming to the classification based on the, here you can see in this diagram, this is how a single mode fiber can propagate, this is how a multi-mode fiber can propagate into the optical fiber. Okay, now coming to the classification based on the refractive index profile, as I said, it will be divided into two types: step index fibers and graded index fibers. Coming to the step index fibers, the core and cladding will have an uniform refractive index. Suppose if I call the core refractive index as mu1 and cladding refractive index as mu2, the core and cladding will have the uniform refractive index throughout the material. But the cladding refractive index, okay, the cladding refractive index should be less than the core refractive index. Mu2 should be less than mu1. Okay, mu2 should be less than mu1. The step or abrupt change in refractive index profile takes place at the core cladding interface. Here you can see the step or abrupt change. Here you can see this is the line where the core and cladding interface. Okay, there is a step or abrupt change in the core and cladding refractive index profile. Okay, this type of fibers are called as the step index fibers. The refractive index plotted along the vertical axis and the radial distance is plotted along the horizontal axis. The core diameter of a single mode step index fiber is 10 micrometers and 50 to 100 micrometers for multi-mode step index fibers. Here you can have single mode step index fibers and multi-mode step index fibers. Now coming to the advantages and disadvantages, the step index optical fibers are relatively easy to manufacture. They are cheaper than the graded index fibers. They have a larger numerical aperture and it has a longer lifetime. The step index fibers will have a longer lifetime than the graded index fibers. But coming to the disadvantages, they have the lower bandwidth. They are having the lower bandwidth. There is more attenuation, more losses of light rays. Attenuation is nothing but loss. There is more distortion, more signal distortion also will happen in the single mode fiber, single mode or multi-mode step index fiber. Now coming to the graded index fibers, you can see, as I said, in step index fibers, the core and cladding will have a uniform refractive index. But here, the core having non-uniform refractive index, while the cladding will have the uniform refractive index. Okay, the core will having non-uniform refractive index, the cladding will be having the uniform refractive index. The refractive index decreases gradually. Okay, the refractive index gradually as we reaches the core and cladding interface. Core and cladding interface. The refractive index plotted along the vertical axis and the radial distance is plotted along the horizontal axis. The core and cladding diameters of a multi-mode graded index fibers are 50 micrometers and 70 micrometers. Okay, these are the diameters, okay, core and cladding of a multi-mode graded index fibers. Now coming to the advantages and disadvantages of the graded index fibers, the signal distortion is very low in graded index fibers. There is low dispersion phenomena will happen, then larger bandwidth, and it is very easy to couple with the optical source. These are very easy to couple with the optical source. Now, but coming to the disadvantages, the graded index fibers having difficulty to manufacture. They are difficult to manufacture because of their fabrication and all. Then they are very expensive compared to the step index fibers. They are of a shorter lifetime. They will be compared to the step index fibers, and they will be having a smaller numerical aperture. Okay, it will be having smaller numerical aperture. Okay, these are the advantages and disadvantages of graded index. Now coming to the advantages of optical fibers, wide bandwidth is one of the main advantages of optical fibers. As the bandwidth is high, the information carrying capacity of fiber is also higher. Okay, the second one is a lightweight. As the fibers cables are made up of silica or plastic or glass, which is much lighter than the copper or aluminum cables. Lightweight fibers cables are cheaper to transport also. Now coming to the other advantages, as you know that the optical fibers are very small in size. Why? Because it will be having only three components: core, cladding, and the coating. Okay, now coming to the availability, these cables are more of silica. The raw materials of the glass is available in plenty. They are available in the earth. Now coming to they are very less cost. Okay, manufacturing of them is also easy. No electromagnetic and radio frequency interferences. Okay, they will be having no electromagnetic and radio frequency interference. There will be having no corrosion. Why? Because they are not made up of like metals or like iron. Okay, they will be having no corrosion. They can be managed in a temperatures of around 800 degrees centigrade, and they are very secure. These optical fibers are very secure. Okay, it is almost impossible to interrupt into a optical fiber okay. Now coming there, these will be having less losses. There will be no attenuation. Okay, fiber optic cables very less signal attenuation over long distance communication. So coming, there will be having more strength. Fiber cables are stronger and rugged. Okay, these are the advantages of the optical fibers.